So folks, here's another video finding the projection vectors. And in this case, we're going to do it in 3 space. I've already worked through the problem, so we'll just highlight the answers. And then what I'd like to do is look at the problem in Calc Plot 3D. So just to reference, this is question number 37 in the textbook. And it corresponds to question number 5 in our My Math Lab assignment. And we're asked to find the projection of vector u onto vector v. And we're doing this for these 2 vectors. We happen to be in R3, but of course the computations here are very similar. So here's the formula for computing the projection vector. So remember, this is a scalar that we multiply then to this vector here. And so I went ahead and did u dot v, and I got the number -12, and I did v dot v, and I got the number 19, and then I just recopied the vector v there, and then I distributed this scalar value to each of those 3 components, and here we have that projection vector. And you can see down below, that's where I did the work for those 2 dot products. So what I find a little bit confusing is finding the scalar component of vector u projected onto vector v. One thing I don't think is clear from this notation is the fact that what we really just want is the length of that projection vector. So I've gone ahead and written it this way. I want you to find the magnitude of that projection vector. What you could do is go ahead and square each of these 3 components, sum them up, and then take the square root, and you would get the same answer as what I'm about to show you. But our textbook gives kind of a simplified version of that scalar component definition, so it can be done a little bit easier. The reason why this is handy is we've already computed u dot v. That was the number -12. And then if we compute the length of v, well, here we have v dot v, and remember that v dot v is equal to the magnitude of v squared. And so since we've already computed v dot v, we know that's 19, so that's the magnitude squared. So the magnitude is the square root of 19, so we get an answer of -12 over the square root of 19. And that's a perfectly reasonable way to leave your answer. Or you could also rationalize your denominator. Okay, so the real purpose for this video was not through this computation, because I actually did this in a previous video, and you can go ahead and take a look at that solution there. And that might be an easier one to see the computations for all this. Instead, what I'd like to do is let's actually look at this in Calc Plot 3D. So here I've gone to Calc Plot 3D. I just Google that and then click the first link that comes up. And what I have the ability to do is to add vectors to this. So I went in and I added 3 vectors, and I went ahead and added each of those components. So let me go ahead and turn each one of these on. So here was our vector u, which was this vector that I'm showing in red here. Hopefully you can see this vector in red here. And then I'll turn on the vector v. That's this blue vector here. And hopefully you can see that. And then careful here, because it's a little bit hard to see, but hopefully you can see that, hey, if I were to take and look at the plane formed between these 2 vectors, and then look at vector v like that, remember that idea of that flashlight shining 90 degrees down on it? That's really hard to do in this case in 3D. And I'm trying to just put this back the way it was. But you can hopefully see that the shadow vector would actually be somewhere behind this vector v, and in fact, if I turn on that projection, there is that green projection vector there. It's on the same span. You can see that's in alignment. That's on the same span as the original vector v, but in this case, it's behind it, and that just happens because, as we saw when we worked the solution, that the scalar component of this was negative, even though this the original vector v is pointing into one quadrant. We're going to be extending the scalar component out in the opposite direction there. So hopefully that gives you a nice visualization. Let's just pull that up one more time for what we're doing as we're computing these vector projections in R3. This is pretty messy to look at, but if you like, I encourage you to go to Calc Plot 3D, actually plot these 3 vectors, or your particular 3 vectors, and see that you've indeed found this green vector here, which is the projection of the red vector onto the span of the blue vector there. I hope this clarifies any questions, but if not, please let me know, and I'll be happy to explain some more.